and tell you actually how to construct the Hauger planar algebra today. And this is wonderful because sort of I've already given you most of the background, and so I can actually spend most of this time just telling you about what we actually do here. Okay, but before I do that, we didn't get quite enough time last time to talk about the graph planar algebra. So I'm going to remind you what that definition is, and just say a couple things about it. Okay, so the graph planar algebra of a graph G. Remember that the vector spaces are made up of functionals from length n loops on our graph. And to define the action of a planar diagram D, so let's say D has k input disks, right? K interior boundary components. And when we talk about G state of D, we mean an assignment that associates vertices to regions and edges to strings in a consistent way. And really, of course, the information of which vertices are associated to which regions can be deduced from knowing which edges go to which strings. But because we're usually working with simply laced graphs, in fact, we will usually only present the vertex information and leave the edge information implicit. Okay, so here's this sort of overwhelming formula, right? That if I have k different functionals as my input to, what letter is that? I think I called it D. Let's keep it as D. Then this planar diagram should produce, again, a functional. And so to say what functional it is, we should give it an input of a particular loop. We'll call that L, and see what we get out, right? So these are all elements of whichever is the appropriate space of functionals. And L is a loop, and numbers match up in the way they're supposed to. So this is equal to a state sum, where we sum over G states of D with the property that if you read this state around the outside boundary, you get this loop L back. So we only look at states that are compatible with this information on the boundary. And now we take the product over each interior disk and see what the functional we've plugged in there does to the loop assigned by the state to that. So sigma of the ith. So let's see if we can think about this and answer the question of what some specific diagrams. Okay, so here's one. All we've done with this diagram is change the position of our marked point. Okay, what does this do to functionals? Okay, and well, maybe more specifically than that, we have a basis for functionals consisting of the Kronecker delta of any particular loop, right? So what does this do to the Kronecker delta for some particular loop L? All right, this is a question for y'all because I already know the answer. I heard rotate. Yes, it changes our base point, right? If our loop L assigned vertices A, B, C, D, E, F, whatever, then this new loop would read F, A, B, C, D, E. Okay, so this is just rotation of base point. Okay, cool. How about, okay, so I've already gotten lazy about chalk color, but this has an even number of points around the interior boundary and 0 points around the exterior. What is this diagram going to do if we give it, again, a Kronecker delta of some particular loop?
Well, it's send basically the vertex you picked to kind of, because a loop here is going to just be a single vertex.
Okay, excellent observation, right? So in particular, whatever we get back is just going to be a single vertex. Whatever that sort of starting vertex is.
Right. Is it going to count, basically kind of count the number of loops starting at that vertex? But maybe it's not quite that, because it has to be kind of a double back loop. It can't just be any random loop.
Okay, so you've said the essential thing here, which is that it has to be a double back loop, right? Whatever region gets assigned, whatever vertex gets assigned to this region has to be the same as this down here. Okay, and since we gave it a particular loop, really what it's doing is it's giving us 1 if this path is the same as its reverse, right? If we traverse the path forwards or backwards and we get the same thing, then we get 1. Otherwise, there are no states on this diagram that are consistent with the data of the loop, and so we get a 0 back. Okay, one more for y'all to think about. What if we have 2 inputs and we connect them up by half their strands? So what would this do to, let's say L is the yeah, so L and L prime are our 2 loops here. What is this diagram doing? So it should produce another functional on the same space, right? So for this particular one that I've drawn, we have a loop of length 8 and a loop of length 8 and a loop of length 8 around the outside.
If they overlap, then it gives you the opposite.
That's right. It's checking if the sort of second half of this. So we'll just write this down verbally. It checks if the second half of L is equal to the first half of L prime, right? That's what these strings connecting L and L prime are doing. And then if they are, it gives you the sort of contracted concatenation, right? The output is the first half of L joined to the second half of L prime.
I have a question.
Mm-hmm.
So I'm just started thinking about what happens if you wanted to have, you had a diagram with no input disks. What's that going to do?
Oh, okay, great. Let's answer that question in just a second. I just want to put a word down here, which is that this is an analog of multiplication. Okay, and this here is a kind of trace. Okay, now let's think about that question. A diagram with no input disks on a graph. So no input here. What is the result of this.
The number of paths that have that shape.
Not the number of paths, but actually the sum of all paths that have that shape. Well, okay, sorry, okay, so remember that this is supposed to give me a functional, right? And so really what I should think is, what if I take this functional and I give it an input of a specific loop L? Then it's either going to give me back 0 if L doesn't have this shape, right? Where like by the shape we mean that I should have put a marked point here, right? But like this diagram specifies that the vertex you start at needs to also be so start 0, 0, 1 needs to also be the second vertex you come to and the fourth vertex you come to, right? And this is telling us that the fifth vertex you come to has to equal the seventh vertex you come to. Okay, and so this is going to give me 0 or 1, depending on whether L is consistent with the regions here.
Then if we had something like with some internal loops or something like that, we could then have more than one being like summing over all the various ones with that.
That's right. If we had some internal stuff here, then we would end up with some sums over all the different things that could be assigned to these interiors. Okay, awesome. So let me remind you why we're thinking about graph planar algebras. Because of this theorem that says that if a subfactor exists, then its planar algebra embeds in the graph planar algebra of gamma, where gamma is either of the principal graphs of our subfactor. Okay. Okay, so I want to tell you just a little bit right now about subfactors that come from planar algebras. Okay, we talked a little bit about the mechanics of how this happens yesterday, but let's take a sort of exterior viewpoint and instead look at the properties that subfactor planar algebras have. For a subfactor planar algebra, we're able to move plenty of the nice structure of the subfactor into the planar algebra. So subfactor planar algebra, P for A contained in B, and let's specify that the index in B of A is finite. Okay, so B is not too big compared to A. Okay, so subfactor planar algebra has the following properties. We have a star on each of the spaces that makes up our planar algebra. Okay, so we have this involution. And our zero box space, one-dimensional. Okay, so it's really just a copy of the complex numbers. And any one of these spaces along the way is finite dimensional. This is why we had to assume that the index was finite. Okay, now here's the big one, that we can define an inner product on each one of our component spaces, given by taking the trace of the multiplication of y star with x, right? So these operations, other than the star, the multiplication and the trace, come from the planar algebra. So we have x, we have y star. We connect up half their strands, and then we go ahead and connect up the rest of their strands. Okay, and so this is a positive definite form. And so that means that we have all of the tools of linear algebra at our disposal. Okay, and I mean, like, you know, not the complicated stuff, the basic stuff, that we can, like, you know, take norms of things, check equality in that way, etc. Okay, and the last thing we get is that our planar algebra is spherical, meaning that we have two different potential traces, right? We could close on the left or close on the right. And these produce equal results. Okay, and in particular, knowing that P0 is one-dimensional is the reason that the trace is just a number, right? Instead of, like we saw over here, this trace would produce a single vertex. This is actually, instead of just describing the properties of a planar algebra coming from subfactors, we're going to define a subfactor planar algebra to be a planar algebra that has these properties. And then it's a theorem due to Serene-Popa in slightly different language. He doesn't actually mention planar algebras. He phrases it in terms of lambda lattices. But if you lift the hood up and look underneath, they're really the same thing. That a subfactor planar algebra will produce an honest-to-God subfactor. Okay, so what are the examples we've seen of planar algebras so far? And do they have this property that they could come from a subfactor? All right, so what about the temporally lead planar algebra? Is it or is it not a subfactor planar algebra? Well, let's see. We've certainly got an adjoint star on each one of our spaces. That was just, remember, the horizontal reflection. And is our zero space one-dimensional? Well, how many diagrams are there that connect 0 points on top to 0 points on the bottom? There's exactly one, right? The empty diagram. Good. Okay, and each of these Pn is finite dimensional. That's pretty clear, probably. But actually, because of some stuff I'm going to tell you in a few minutes, I want more than that. So, okay, maybe we should organize our thoughts a little bit. Adjoint check, that was built right in. P0 is one-dimensional, we're good. What is the dimension of the nth temporally lead algebra? Bad notation, I should be writing TL here.
Depends even or odd.
Okay, good point. What if n is odd? Then it's 0. So if n is even,
parentheses.
Hmm?
Number of parentheses.
Yes, right. So if n is even, this is, sorry, if we have TL2, and this is the nth Catalan number. Because we have a bijection between a pairing of points around the boundary of this circle and parenthetical expressions by, you just read around the outside of your circle. And every time you encounter a string for the first time, you write an open parenthesis. And every time you encounter a string for the second time, you close the parenthesis. So this diagram corresponds to this parentheses word. Okay. And in particular, these are finite. So we're good. What else? Positive definiteness of the inner product. Well, without going into detail here, this is always positive definite. Remember, we had quantum 2 being our loop factor in the temporally lead algebra, as long as this is bigger than 2. And in the subfactor cases that we care about, as long as our index is more than 4, this holds. So, okay. And finally, what else? Sphericality. When we take a trace of something, we no longer have any unconnected strings. We just have a whole lot of loops. It looks like a plate of SpaghettiOs, right? And it doesn't really matter how much you stretch these SpaghettiOs, you still have the same number in the end. So drawing this like this or like this doesn't change that number. So spherical it is. Excellent. Okay. So, yeah, Temperley-Lieb is a subfactor planar algebra. And more than that, it's in some sense like the universal subfactor planar algebra. It shows up as a subplanar algebra of any other subfactor planar algebra because of this thing that we were just talking about, that any Temperley-Lieb diagram is in particular a planar diagram, and so should have an interpretation in that planar algebra. What about the second example of planar algebras we've been looking at? What about the graph planar algebra? Does this give us a subfactor planar? So what do we think should play the role of star, our involution, in the graph planar algebra? Well, if we think about what we've been doing over here, and we think about star on diagrams being a horizontal reflection of diagrams, then we really want just to reverse our paths, right? Read them back to front instead of front to back. So we're good on that score. Is our zero space one-dimensional? Not even close, right? Our zero space has one element for every vertex on our graph. And so it's finite, but it's certainly not one. Okay, now this seems bad, but it's actually good. In the following sense, every other one of these axioms works. Okay? So what's going on here is that we have a planar algebra that is slightly too big to be a subfactor planar algebra, but has everything else in common with subfactor planar algebras. So if you think about it, that's important for this theorem, right? That it's a bigger space where we can look for our subfactor planar algebras. And in particular, if you find something in here that's a planar algebra and it's one-dimensional, it should inherit the rest of this structure pretty easily. Okay. Everything else here checks out. Up to some of these will require a little bit of interpretation, right? Because if P0 is not one-dimensional, writing these statements down seems a little iffy. Ignoring that for now. And so we're going now to hunt for the Hogerup planar algebra inside the graph planar algebra of its principal graphs. So let's remember what those graphs were. We have the more symmetric graph and the less symmetric one. And they look like this. Okay. What can we say on the basis of these principal graphs? It turns out the principal graphs contain enough information about the planar algebra that we'll be able to zero in the graph planar algebra on a copy of Hogerup. So, okay. This is all still sort of hypothetical. Okay, so if the Hogerup planar algebra exists, then Temperley-Lieb at the particular value of Q that makes quantum 2 into the root of 5 plus root 13 over 2 is embedded in this planar algebra. Okay, this is Temperley-Lieb exists inside any subfactor planar algebra. And so if now Temperley-Lieb at any value more than 2 has as its principal graphs just an infinite chain. Okay, and that's the other principal graph too. This, by the way, is what we talked about the other day about the Jones-Wenzel projectors inside temporally Lieb. That these vertices correspond to these Jones-Wenzel projections, but I'm not going to get into that. I draw this because what I want to claim is this. That for the first few steps, the Hover-up planar algebra looks like the temporally Lieb planar algebra. That there are 3 vertices along the way where you have nothing more than you have here. Okay, because these projections still exist inside Hover-up planar algebra. And what the principal graph is saying is that they are minimal up to this branch point. Okay, and now the fourth space here, H4, which is what we see at this level, is 15-dimensional. Okay, and the fourth Catalan number is 14. And so we have finally something new coming in at this level. Okay. And so in our so far hypothetical Hover-up planar algebra, we know that we must have something in H4, which is genuinely new. And so I'm going to say that we choose it to be orthogonal to the temporally Lieb stuff that we've seen so far. Okay, 15-dimensional space. We want to pick some element here so that it and TL4 generates the whole space. And so why not take something orthogonal? And more than that, let's also take it to be self-adjoint. Now, okay, we actually know a ton of stuff about the things we can get using S and different planar algebra operations. Okay, for the following reason, that if we started with this generator S and we took its rotation, okay, and now what we get back still has to be inside this 15-dimensional space, right? So we can say that this really should still be in the span of S and temporally Lieb, but because we took S to be perpendicular to temporally Lieb, in fact, it turns out that this gives us just some multiple of S back. Okay, so S is an eigenvector for the rotation operator. And now my possible eigenvalues are 1 and -1, I and -I, if I'm rotating 2 out of 8 strands. Oh yeah, I should say that because of the fact that we're working with a subfactor, we only ever have stuff in the even with an even number of strings. And so when I write HN, I really mean things that have 2n strands in this planar algebra. Okay, so it turns out that the sort of understanding the details of the principal graph better can tell you that the eigenvalue has to be -1. Okay, but this isn't even close to everything that we can say. Okay. From this statement that S is perpendicular to temporally Lieb, we can conclude that if we have an S and we put a cap anywhere on its outside, we should get back 0. Okay, and that's true for any position of this cap around the perimeter. And more than that, and I promise I will stop soon, but you can just kind of keep chasing down these consequences of the fact that planar diagrams the whole infinitude of them only give us a 15-dimensional space, and we already know what 14 of those dimensions are. So if we took 2 copies of this new thing S, and we multiplied them together, then we would still be in the span of TL4 and S. Okay, and more than that, we can actually work out the details of what this relation should be, but for the sake of what's coming later, I don't really need more than this. Okay, that this is a reduction relation on my generator, right? If I have 2 of them and they're joined up by 4 strands, then in fact, I only have at most 1 of them. We can keep doing this, or variations on a theme with this, and it's hard to know where to stop. So what I'd like to do is just tell you the list of relations that it's necessary that everything else follows from. Okay. And so the theorem, and I'm quoting from a paper with Bigelow, Morrison, myself, and Snyder, is that there exists an element S with these properties in the graph planar algebra of either of these principal graphs with the properties. Now, we've already written some of these down, so that it's an eigenvector for rotation, and that it's uncappable for all positions of the cap. And the particular multiplication relation we have is that, in fact, when we square this generator S, we get the 4th Jones-Wenzel idempotent in this graph planar algebra. So even better than saying it's somewhere in this span, we can say exactly what it is in this span. Okay, and now the other relations I need are that if I have S with a single strand over the top, there's a relation that lets me replace that with 2 S's joined like so, with 3 strands between them, plus some lower order terms. Okay, and we'll get to why lower order terms is the right way to think about this in a minute. But just for now, you should
question.
think of lower order terms as being diagrams that have 1 or 0 S's where S does not have a string over the top.
Where are the marked point regions?
I was being a little bit ambiguous about that. I think you can put them here and no, not there. We'll put it here. And I should mention that there's some non-zero coefficient up front. Yeah. Okay. And then we actually have a similar relation if S is underneath 2 strands. So we have some non-zero coefficient. And now we have 3 of these and lower order terms, and I should find somewhere to put these dots. Doesn't really matter. Okay. Now, what's going on here is that really subvectors are shaded planar algebras, okay? That the planar diagrams I'm drawing should have a checkerboard shading on them. And that's because remember that the subfactor, when we looked at, say, the principal graph, we were looking at 2 different kinds of things and how they fit together. modules. Oh, well, everything was a bimodule, right? But we had both AA bimodules and AB bimodules. Okay, so that gets really tedious to draw on the board, so I'm not doing that. But that is, for example, why we have a separate relation here in addition to this one. In fact, I think I wrote this one down wrong. Right? Because you would think, right, that if I can pull a generator past one strand, I can pull a generator past two strands, right? But in fact, because of the two different kinds of shading, I need both these relations. Okay, so the theorem is that with these 5 requirements, we can find an element in the graph planar algebra that satisfies these, and the planar algebra generated by S is the Huggerem planar algebra. Okay. So right. So I've told you a little bit about the graph planar algebra so far. What I haven't told you is how we can be sure that having found something that satisfies these relations is enough to guarantee that we get these principal graphs back. Okay, and actually, a lot of that work is Uwe Huggerup's classification of possible principal graphs. It tells us that once we know that we have a subfactor planar algebra at this particular index, and it's not temporally leave, then it must be one of those. How do we know the planar algebra generated by this generator S is a subfactor planar algebra? By the way, when I say the planar algebra generated by S, I mean take all the planar diagrams you can make with any number of copies of S in them. Okay, so we could have 0, which just be in temporally bland. We could have 1, we could have 2, we could have however many you can fit in a diagram, as long as each of your S's has 8 strands coming out of it. Okay, so potentially a very large space. But we've imposed relations, and these relations cut our dimensions down sufficiently that we end up with something which is a planar algebra. So remember that the graph planar algebra had almost everything we needed. The one thing it was missing was this fact that the 0 space was too big. And so really the question here is that if we look at the planar algebra generated by S and the associated 0 space, that this is one-dimensional. Okay? More practically, we're saying that any closed network made up of copies of S is a multiple of the empty diagram. And so the proof here is going to be to give an evaluation algorithm to tell you how to take a bunch of these S's connected up arbitrarily and produce a number which is the multiple of the empty diagram that it corresponds to. Okay, people feel good about this as our goal? This is what we want to do at this point? Good, then let's do it. Okay, so this is, I'm going to go use this board over here. This is Stephen Bigelow's jellyfish. Okay, so we start with, all diagrams from this point on are going to be very heuristic, okay? Correct maybe in the idea, but none of the details. We have a bunch of copies of our generator S connected among each other in various ways. So imagine that I have drawn this in such a way that all of the strings add up to 8 around every vertex, okay? And so how can I use these 5 relations to turn this into some multiple of the empty diagram? So what I'd like to do is I'd like to first get the interior of my diagram emptied out. Make it so that all of my generators are around the exterior. And then I'll argue that we'll be able to apply our, where to go? The multiplication relation. Then we'll be able to apply the multiplication relation to cancel out pairs of them. But as you can see from this picture, I have, in this example, 3 that aren't actually on the outside. So the first thing I do is I choose a path for each of these to the outside. And now what I do is I apply relations 4 and 5 over here. Okay, and these are, we called these the substitute braiding relations. Because this is very much a not braided category, but we can use these in the way that you might use a braiding to move things where you want them to be. Okay, so this has to pass through some number of strands to get to the outside. And we just apply this relation however many times we have to. Okay, and you know, maybe it's a little bit unpleasant, right? Maybe we get a lot more of these copies of our generator. Maybe we get a lot more terms. It stops being a single network and starts being a sum of a bunch. But anyways, we do that enough times and we end up with some collection of generators arranged around a circle. Okay, and they're connected to each other, but it's still planar. Okay, and now the claim is that somewhere in here, there's a pair of generators connected by 4 or more strands. Okay, and in this particular picture, it would be either this one, or this one, or I've drawn this strangely, but either of these two that we can zoom in on. Okay, because we have a triangulation of a polygon, really. And therefore, there's some vertex which is only part of one triangle. Okay, our n-gon gets broken up into n-2 triangles, and so there's at least one triangle here, which has a vertex that's part of only that triangle. Okay, so pigeonhole principle, one or the other direction has 4 strands coming out of it. Okay, so we identify this pair of S's connected by 4 or more strands, and we use our multiplication relation. It's the relation 3 up there that says that we can cancel out a pair of these and replace them by Jones-Wenzel idempotent. Okay, well, we do that, and then we have, again, something that looks like this, right? A polygon, fewer copies of S around the outside, a bunch of data of the connection. And so we can keep doing this. Okay, and so we repeat this cancellation until there's either 0 or 1 copy of my generator left. And at that point, if there's 1, it must loop back on itself somehow, and so we get 0, according to relation 2 there. And so we end up with something that's just intemporally lead, and we evaluate that, and we get a number back. Okay, and so the important thing here is that we have an evaluation algorithm, and our evaluation algorithm doesn't sort of has this step where it makes things more complicated before it simplifies them. That maybe, you know, you'd think that we should only ever use reductive relations. So if we see 2 S's connected by 3 strands, replace them by a single S. But in fact, if we use this relation backwards and our evaluation algorithm has 2 steps, then first we bring everything to the outside, and then we're guaranteed to be able to cancel things in pairs and end up with a single number. Okay, and so that is how you prove that the Hager-up planar algebra exists. And the last thing I'm going to say is that, in fact, this works for extended Hager-up as well. Okay, so this same theorem goes through for extended Hager-up. So what is extended Hager-up? It's the same principal graphs, but we've added 4 edges at the very beginning. Okay, so when Hager-up classified these potential low index principal graphs, he came up with a list that had 2 infinite families in it and 1 exceptional thing. He and Marta Asaida constructed the exceptional thing and one of the things on this list. And then over the next 15 years, people sort of gradually knocked off the rest of the stuff on the list using algebra techniques like associativity of the fusion rules implied by the graphs, or later on number theory techniques, until the last one that was unknown was this one. Okay, and so this construction works for the extended Hager-up subfactor exactly as well as it does here for Hager-up. The difference is that I'm not going to do this, but you basically have to draw 16 strands on each of these S's instead of 8 strands. But then, in fact, up to the fact that your value of quantum 2 is a little different, so your coefficients are slightly different, it all goes through exactly the same way. And so maybe I will leave you with an open question, which is why this doesn't work for bigger things on the list, right? So we know for number theoretic reasons that if you took the same graph and added 4 more vertices at the beginning, there would not be an associated subfactor planar algebra. So there's not a tensor category there. But the work that shows that these relations have to be present works just as well for any number of initial vertices. And so if you just deal with that as a abstract planar algebra, it must be true that once we have 24 vertices 24 strings instead of 16 strings, that these relations introduce an inconsistency somewhere. Okay, but a diagrammatic way to understand why these further extended Hager-up categories don't exist has not been found yet. Would be very interesting. So I will leave you with that.
Is there any question?
Yes.
Yes, for you.
Yes. So the number theoretic reasons that you mentioned does it have to do with this dimensions being non-cyclotomic
Yes.
or something like this?
Yeah, that's exactly it. That the dimension of the generator is not a cyclotomic integer.
So can one just imagine that in the slower Hager-up things you get like kind of small degree equations, and then you get kind of larger, polynomial equations, because statistically, if you pick like a random polynomial, then its roots are not going to be
That's right.
cyclotomic.
The question is how to see that diagrammatically, right? So, if this doesn't exist as a subfactor planar algebra, then it should be true that if we introduced a generator S and imposed the analogs of these relations, there must be some diagram that evaluates in 2 different ways to give you the answer that everything in your picture is in fact equal to 0.
But these relations, you cannot really think about them like as sort of polynomial, right? By any stretch of imagination.
I don't even really know what it would mean to assert that they were polynomial.
No, me neither. So.
Right? Because, if we just take the abstract subfactor planar algebra with the closed loop value that's implied by the principal graph and these 5 relations.
Okay, understood. Thank you.
So my question is, so you said that there has to be some sort of inconsistency when you add more strings. How can you show then that there is an inconsistency with I don't know, like if you say
Did you say how can you show there's not an inconsistency
in what you've done before with
that's why the graph planar algebra is so important, Okay, because we don't just construct this abstractly by taking a generator and quotienting by these relations. We find a generator in the graph planar algebra, and we can show that it's non-zero by taking its inner product with itself and getting a non-zero number back. Right, and so that's what the graph planar algebra does for us. It gives us this concrete place to go looking for these subfactor planar
I see,
algebras.
that makes sense. Thank you.
You're welcome.
Other question? We start again. Thank you.
All right, thank you.